Complete that program of C++ where we were adding two polynomials. You can check everybody completed. So anybody could complete? Some of you. Adding the two polynomials. Yeah, if you have not, so your test cases also. Very good. '81 have finished, and another 120 plus 10, 111 have tried totally. Because it was, we had discussed the question, we had given most of the solution, and only thing you were left to do is to complete. I'm not looking at the 81, I'm looking at the 20 and 10, which is also not done. And then there is this whole remaining people who are, I don't know. Okay, we can't do much, and I will not do much. Okay, so we will continue with the linked list. So today we will do something very simple. So we will start. I will do two very straightforward things today. Most probably you will find them on Google also, but don't depend on Google to find the solution. So we will start with, you are given a linked list of some kind, and we will take our old linked list and try to modify it. Now you're asked to do a particular thing, that you're asked to write a method on linked list which says insert, and this is a method on the linked list. So it says insert, and the first one is the position at which you want to insert. So let's index the positions as 0, 1, 2, 3, or you can say 1, 2, 3, 4, doesn't matter. I'm just using the indexing 0 based. So 0th is the first element of the list, 1 is the second, 2 is the third, and 3 third is the fourth. So I will say something like insert at position 1 a value 25. Okay. So let's pretend that the values here are 5, 10, 15, 20. So I'm saying insert at position 1, that is after position 1, or you can say at position 1. So it means here after position 0. So the list after your insertion should look something like this: 25, 10, 15, and 20. This is how the list should look like: 5, 25, 10, after the insertion is happened. So these should get pushed ahead. Okay, and then if I say insert at 0, 10, then this should look like, let's make it 11, 11, 5, 25, and so on. So this is at position 0, I want a value 11. Okay. Now there is one more special case where you say at, you can say position 3. So 0, 1, 2, 3. So position 3. So if I say insert at position 3, 28, then the value should get inserted over here. That is not here, at this position. So this should become 28, 20. This is 20. So this is at position 3. So we have to insert at that appropriate position. Okay. So this is the code we have to write. So we are given a value, and we are given a linked list. We have already prepared a linked list, let's say. And in that we have to call this function, this method. And we have to write this method. Fairly easy to write. Okay. So what we'll do is, first I'll write it with you to a certain extent, then hopefully you'll complete it. This is a very standard method, but we need to do it. Now, whenever we do this kind of questions, we have to understand that when you're doing an insertion in a list, are you inserting at 0? So that is a special case, because when you're inserting at 0, what are you doing? You have to change the head pointer. That is the only place where the head pointer is going to change. Because when you are inserting at position 0, the new head pointer will point to that 0th element, and then the rest of it will follow. So that is a special case you have to take care. Then another case you might want to take care is that if I give an insert at 10 and that is beyond the list, then what do? There can be two options. One is you insert it at the end of the list, or you say simply that there is not possible to insert at position 10 because the number of nodes in the list are only so many. Okay? So let's say we have to take care of both these conditions. That is, go beyond. If it is beyond, we say it's not possible, and that's it, end of the story. If it is within, we insert accordingly. And if it is 0, that's a special case. So whenever you think of a problem, you have to think what are the boundary conditions. Boundary conditions means the special cases. Do I have to do something different if it is at 0, if it is beyond, and something which is in between. So these are the three types you have to think of the logic and do. So let's see where we are on insert. Let's go back. We have written some code on insert or something. In our practice question we had append. We had append. Append is fine. So we had that. Okay, let us see if we can get that. Take your time. So we'll just wait if you can pull the first question. If you have the first question with you in your practice, then you can work with it. See, in linked list, we need to have all the previous questions available. No? No, you should look at new code, whatever they had written earlier. Searching for, I will make a change to our old code. Okay, now suppose for insert to work and to check whether it is end of the list has finished, you will have to make a small change. In our linked list, so we are having a class linked list. So far my class linked list, I am not writing the whole class, looks something like this, where I have to make the change now. So far it had a head pointer, node star HPDR. Okay, that was my head pointer. We had this already. Then we had, sorry, I have to put the public. And then I had a whole bunch of fields here. Besides the node dot, no, I didn't have a whole lot of fields, I had some methods. So the methods I had were, I think, we had we didn't have a constructor. We just said this is equal to null. So we didn't use a constructor. Then we had a method here called append. And what was append doing? It was taking a value, let's say int and a, and it was doing something which was appending to the end of the list. That's all. We had one append method and we had a display method which was displaying whatever is there in the linked list by iteration. This is what we had. So now what we are going to do is, We have this already. This code is already there. I think they are trying to find it. Eventually we will find it. Now, I'm going to add one more field here. Can you guess which field? To keep track whether we are going to exceed the insert position, or we are trying, suppose the list is only four elements and I am trying to say insert 7. Obviously the code should work. So how do I take care of that? So I should remember what is the current length of the list. What is the maximum number of nodes in a list, length of the list. So I am going to introduce a field called int len equal to 0. Okay, I am going to introduce this field. This len gives me the size of the linked list. So I have this field. Now, what am I going to do? Whenever I am doing an append, whenever I am adding something to the list, what will I do? After I am appending, I will say length plus plus, because that way this length can keep track of how many nodes are there in the list. So this will be useful to us when we are implementing insert. So we'll make a small change in the existing append method. We'll add a new field called length, and we'll say every time we append a new element, we'll increment the length. That is pretty straightforward, because at any given time you can also see the length if you want, or you can use the length. So then, with that in mind, we can write a insert. Okay. So this is the code that we have for display and for each node. Okay. So let's see whether everything is okay. 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 Looks okay. I don't know whether you have this code. You have? You don't? No. My suggestion is always when you write practice question, please comment out the earlier code so that you can decomment it and do it. If you have not done it, then I think you'll have to just watch for some time. Okay. Now let's write an insert. But as I said, before writing an insert, we'll need to keep track of how many nodes are there in the list. So we'll make that change. How do we make that change? Go up. No, I think before that, I should ask you this question. Do any of you have this code? You have? Some of you are quick and alert. Some of you are just not understanding what to do. So, see, whenever we are writing code, if you are writing in practice 1, just comment out code. If you are adding something to that or subtracting something from it, don't remove the code from your tool, from your editor. Just comment, and don't tell me you don't know how to comment. Okay? You just have to put a / star and / slash. That's all you have to do, so that the code is there with you. And we can use that code again, because we'll keep using this code again and again, and there's no point just doing typing practice and typing the code again. So that is if you have the practice one. No, I'm not sure whether they have. Some of them have. Okay. Or you make it available as a standard question. Okay, this is another way where we can give you that question. The code so far. I think let's do that first. Okay, we'll give you this code so that you will get a ready-made question, whatever it's called. Practice Lab 3. If you can open Practice Lab 3, then you are on the same page as we are. Are you able to see Practice Lab 3? Are you able to see our code? So all of us are at the same point. Yes? So we will start. You have to add some things today, some 2-3 problems you have to do. Okay, so I think this is the thing we should do. We should give them the code beforehand, I mean like this, so that they have the... Okay, so the first change I'm going to do is, I'm going to go to class linked list. There is the class linked list in which we are going to add an extra field called length or size, whatever you want to call it. So int length equal to 0. Okay. And whenever we are adding a node at the end of append after 52, Here we'll say length plus plus. Okay. So whenever we add a node, append a node to our list, we'll just keep a track of a length. Now we are ready to write the insert operation. So we'll write it very slowly and very carefully. Okay. Please try and follow. So first we will have to create a method called insert in the class linked list. I am in the class linked list. Okay. So there I am creating a method. Now first thing you have to think is, should insert method return anything? Not necessarily, because we don't expect anything to come. It will just add to the list. Anyway we have HPDR. And if you are adding at the beginning, the HPDR will change. So there is not much of a problem. Okay, so we don't have to return anything. So we will say void. Then insert. Now we must think, how many parameters should insert take? Okay, we said insert should take 2 parameters. Why 2? First is at which position you want to insert. Second is what is the value you want to insert. So both are ints in our case, because every element in our list is an integer. So we will say int position, and V stands for value. Two things, position and value. Position is where you want to insert, and I have given you an interpretation of the position, and value, which value do you want to insert. That is what you need to do. Okay. So now, what are the things that you have to examine? So we have to check what is P, position, correct? So that if position is 0, we would like to do something. If position is greater than the length, then we have to do something. Things like that. Okay. So what we are going to do is, we are going to check if position P equal to 0, equal 0. That means what? This guy wants the node to be inserted right in the beginning of the list. So what should we do? So we should create a node first. That is obvious. Without creating a node, you cannot put it. So you'll get a NPTR. So you should say node star NPTR. I want to point out to the node. Node star NPTR is equal to new node with V. Okay, let's do that first. Let's do that. Okay, let's do it here. Doesn't matter. Node with V. Parameter V. Okay, so does everybody agree with line 58? You're not done yet. Is it correct? Line 58, yeah. We are saying if P equal 0, we are creating a new node first. Where is the new node? NPTR is pointing to new node. So new node is getting created somewhere in memory, and NPTR is pointing to that. We have that. Now what we need to do? Now, remember, this node needs to go at the head of the list. So what should we do? The HPDR that we already have, we may have, is going to be our next. Do you agree? This node's next is going to be HPDR. If this is the first guy to be getting inserted, then it doesn't matter. So if HPDR, okay, so what will we do now? We know we have to insert at the beginning. So I will say NPTR1, whatever you have declared. NPTR1's next is equal to HPDR. Whatever was the old head pointer, whatever it may be, next pointers, NPTR's next or NPTR1's next is equal to HPDR. Does everybody agree? So what I have done? I have created a node and I have made the node point to the old HPDR. Now what should I do? One step is left. I have to update my HPDR to the NPTR one, because now my head has become the new NPTR, whose next is the old HPDR. So you understand what I am doing. I am taking a node, creating a node. I already have a HPDR of the list. So this new node's next, I am making it as HPDR. So that got connected. But my HPDR is going to change. So my HPDR is going to become this guy, the one node which I created just now. So I will say HPDR is equal to NPTR1. Over. Over? No, not over. For I have handled the case for P equal to 0. Yes? let's handle the case for if P is greater than N, or I should say, see, if your list is having N elements, then the last index you can insert is at N minus 1. You are with me? No, yes. If you have N elements, the last position you have is, you are having positions from 0 to N minus 1. So, if the position given is greater than N minus 1, you cannot insert. Or you can decide that I will insert at the end. Are you with me? That is our decision. You can say I refuse to insert because there is no such position. So let's take that view. That we don't want to insert. If you give me there are only 4 elements in the list and you say insert at 10 element, I am not going to insert. We are not going to have that. Okay? So we will say else if P greater than length minus 1. Last viable position for me to insert is length minus 1. After that I cannot insert. So if P is greater than length minus 1, what should I do? Give up. I should say see out. Not possible to insert. Or insert out of bounds. That is how we normally report that. Else is, so I have taken care of the special cases. Always we have to watch out for special cases. Special cases are crucial. So now we say else. Else means it's not 0. I have not taken negative cases. I am assuming we can handle that also. Insert at some negative position. We are assuming that that is not given, or you have to take care of that. If P equal minus 1 or P less than 0, just say insert not possible. Same thing. Or you can add it into that condition itself. Correct? So let's ignore that for the time being, that we have only sane programmers and they will only insert positive positions. Okay. So else, now I have to insert at a particular position. Okay. So let's think of it. So let's say I want to insert at position number 3. So what I should do? If I have to insert at position number 3, let's understand the mechanics and then we'll do it. Okay. So yeah, let's look at this. So this is my linked list. Okay, so this is position 0, 1, 2, 3. So my insert is given as position 2, some value 10. This is the value to insert. So values, let's say, are 5, 6, 7, 8, whatever. So now here I have to insert. So from the head of the list, I will have to position myself here. Correct? That is one value earlier than the position at which I want to insert. I have to position. So if I have to insert at position 3, I have to reach node 2. So I have to reach node 2. So if I have to reach node 2, how do I reach node 2? How many times I have to go forward? So I have to go forward, I am at 0. First time I go forward, 1. Then 2. So if I have to reach position n, say position 2, I have to scroll forward 2 times. Do you agree? Yes. Everybody agrees that, see, I am inserting something at position 3. That is what, at position 2. Sorry, I am inserting at position 2. That means I have to stop at 1. So, I have to trace back a little. So how many, I am already at 0. I will always be positioned at 0. That is the head point. So how many times do I have to move forward? 1 time. So if the position that I am trying to insert is 2 or P, how many times I have to move forward? P minus 1 times. You can work it out in any other way, but I am just making it simple. You have to move forward P minus 1 time. Then only you will be at the right point. So if you are inserting at position 2, I mean you want to insert at position 2, you have to get to position 1. How do you get to position 1? Move forward 1 time. That is P minus 1 time. Does everybody buy that? Think a little. If you have to insert at position 4, you have to get to position 3. To get to position 3, you have to move forward how many times? 4 minus 1 time. That is 3 times. Because first time you will move from 0 to 1. Second time you will move from 1 to 2. Third time you will move from 2 to 3. Correct? So P minus 1, you have to move forward that many times. Does everybody agree? Unless I move forward P minus 1 times, I will not be at the right point. So how do I move forward P minus 1 times? I write a small loop, correct? Keep a small count and keep moving till I am less than P minus 1. The moment I am equal to P minus 1, I should stop. Yes. Okay. So let's see whether we can write a good loop to do that. Else, let's introduce a variable there called count. Int count. Int. There are better ways of writing it, but I am just int count equal to 0. You know why I am using count? To decide how many times I should move forward. So, while count less than P minus 1. I should say, while count less than P minus 1, what I should do? Move forward. How do I move forward? I should declare temp equal to HPDR. Remember, you should not disturb HPDR. Never disturb HPDR, otherwise you lose your pointer to the linked list itself. So say temp is equal to, we have to say this outside. Temp is equal to HPDR and just say temp is equal to temps next. That is how you move forward. Okay. So above that, let's say node star temp T, okay, is equal to HPDR. Then what am I doing? While count less than P minus 1, yeah, I say T is equal to, T is next. Do you understand why I am doing what I am doing? So I am saying while count is less than. So I will come out of this while loop when what happens? When count becomes equal to P minus 1. Remember I started at 0, 1, 2. Am I correct in my counting? Oh yes. So I am not doing for P minus 1. So let's say if P is 2, okay, P minus 1 will be 1. So first time 0 will be less than 1. Correct? I will move forward. I have to move forward only 1 time because I am inserting at position 2. So I have to position at 1. I am getting there. You work out your logic, you will get there. So now, what has happened? My T, that is temp pointer, is correctly positioned. Would you agree? Remember, I have to position myself one position before. Do you understand why I am positioning one position before? Because remember, I'll give you the justification here. Yeah, I am positioned here. Why am I positioned here? Because now this guy has to be inserted. So I'll create a new node here and then I will create a node with the value 10. I'll create this node and its NPTR will be something. Then what will I do? This guy is where I am positioned. Its next is right now here. So I'll have to preserve that next, otherwise I'll lose that next. So this guy is next, I have to preserve somewhere. Let's say I create temp is equal to T is next. My T is here. Okay. This temp is also a node pointer. My T is here. So temp is T is next. So temp points where? Temp points here. Okay. Right now temp is pointing here. Do you agree? I am going to create that. And then what am I going to do? I have already created this node. I have to write code for that. And then what I have to do? Then I have preserved T is next. Now I have to say T is next is equal to whatever that new node I have created. So now this will happen. But what should happen now? One more thing. This guy is next should become this guy. So then I have to say NPTR's next is equal to 10. Not T. Yeah. So these three steps you have to understand. See, I am positioned at 1. Just think in your mind. It's not very difficult. I am positioned at 1. I have created a new node with the value 10. Correct? Now I have to bring that guy right after 1 and before the old 2. Correct? So what should I do? I have this new guy. Now I take this wherever I am positioned. I have to first preserve my next, because that next guy whom I am pointing to next, the old 2, I have to preserve. So that is what I am doing by saying temp is equal to T is next. Preserve means keep it somewhere. Otherwise T is next will be wiped out if I don't do that guy. And T is next, if it is wiped out, I lose the next guy. I have to get that next guy. So temp is equal to T is next. I got him. Having got that, what am I doing next? T is next. T is where I am positioned currently, where I am sitting. So T is next is equal to this new node I have created. So that is how that pointer which is going down, I have to connect. Then to this new node, what should be its next? Its next should be whatever T's next was earlier should become now this new chap's next. Then only I will come in between. So in the last line, what am I doing? Third line, NPTR, that's the new guy I created. His next, yes, should be equal to what I have preserved, temp, should be equal to temp. That is the previous next. The current one's next was that 2. So that should become now my next, the new node's next. I think this is fairly easy. If you see the figure and see this, you'll understand it in no time. Because what we are doing, we have positioned ourselves at that 1. We are at 1. Think we are at 1. We created a new node. Now, my next, I have to keep it somewhere. That is temp. Then, my next should become this new node. And that new node's next should become temp. Okay, so this is how you are now juxtaposing. Juxtaposing means getting in your node in that list. So we have taken care of 3 conditions: beginning, beyond, and in between. Okay, so we have taken care of those situations. So let's go ahead and write this code. So, okay, now I am correctly positioned with my T. So, yeah, we have to create a node. Okay, T1 is a new node. Node star T1 is equal to, I forgot to do one important thing in the loop. I am looping perpetually. I have to say count plus plus, no, as I move forward. Otherwise, count will never reach that value. Right? So we forgot to say that. Good. So node star T1 is equal to what? New node, whatever you are creating, new node with that parameter which was given, that new data node V. Yeah. So with the value we had to create, we are saying node start T1 is equal to new node V. We have created a new node. Yeah. Now we have to bring him into the chain. So how do we do it? We say temp is equal to, reserve the pointer, this is a new guy. Temp is equal to T's next. You are understanding why I am doing this? I have to preserve my old T's next I have to preserve, otherwise I cannot make the chain complete. So node start temp is equal to T's next. Then I will say T's next is equal to T1. That is a new chap. T's next is equal to T1. That is now I have connected the previous guy to the new node. What is left? This new node's next should be the previous guy's next, which is in temp, which is sitting in temp. So T1's next is equal to temp. That's it. So we have got our list made. Do all of you agree with my code? We have inserted in the beginning. We are refusing to insert after the length. One more step is left. Can you tell me what I have missed in insert? Sorry? No, greater we have handled. Something, just one line we have missed. When you insert a new node, what should happen? Sorry? Length, not increment. See, I have got a new node into the game, no? No, yes. So my list size, whether I bring in the beginning or at the end, in any case, all the cases, I should have length more than one, no? Okay. So, no. Will you do it in every case, or you can do that if you are going to do a return there? No. After that out of bound, then you should say return there, isn't it? Because you don't want to proceed, just return. Do you agree? Then we can say length, or otherwise what you have to do? In both the cases where we are inserting, we have to do length plus. Okay. Now that I leave it to you. So else we have to say after we have inserted at after line 76, put length plus. Or now we can put it and go up. When you add in the first also, the length has to go up. No? Even if the first node is added at the first position, then also length should go up. Okay, so we have done something. We have added insert. We'll go through it again. But before that, let's try it out. See whether we have any bugs, clear them, and then we'll go through the code again. So, okay, main, you now say L dot insert. Now first is position. Say 0, 1, 2. Just say 2 and say 30. Okay, then say again L dot display. So we are inserting and then again checking. Before that also we are checking. Yes? Okay, let's see whether we are fine. Let's try to compile it first. We should have given a insert? 5, 10, 15, 20. Before, no, that should be, no. This is after insert. Okay, let's see what we get here. Run it and check and then see how it's going. Yeah, so remember we are inserting at position 2. So we are saying initially my list looks like 5, 10, 15, 20. And then I am inserting a value 30, I guess. So 5, 10, then 30. It is inserted at the correct slot. And then we have 15 and 20. Okay. Now let's try one more thing. Let's say we insert at 0. We have to try out that one. So, okay, we are inserting at position 0 to just check whether our code is okay or not. So let's run it and check. Yeah, as expected, when our original list is at the top, and when we are inserting at position 0, we are getting 35, whatever, 10, 15, 20. So it has gone in the right slot. What is the other check we have to do? Now there are 4 elements in our list, original list. 4 elements are there. So I have to insert only in position 0 to 3. Okay? So if I give 4 or more, it should say I can't do. Okay? So let's try 4. Yeah. So we got insert out of bound. It did not insert, and the old list is preserved. Did you understand? Old list is as it is because it cannot insert. It was not possible. Then we will try one more condition, whether the insert at the last is happening or not. So instead of 4, we'll say 3. So 3 means what? At position 3, remember our list has 0, 1, 2, 3. So at position 3, we have to insert. So let's see whether that works. It didn't work. It worked. 0, 1, 0, 1, 30. Yes, it inserted. Yeah, it's working. For all envisaged conditions, it's working. Yeah, if you are able to get it to work, then you are with us. You are getting everything to happen. Okay? So I will give you 5 minutes. Please get that code to run, because then I will move to the next condition. So we will pause for a few minutes, give you an opportunity to run. Because after that we can give you the code so that we move from that step forward. If you are not able to do, we have practice 4. If you refresh your console, you will see practice 4. The same code what we wrote. Okay, you can go through the code in case you are not able to complete it on your own. For those of you who are a little late, Latif. Now we learn how to delete a node. Now, how will we delete a node? We'll get which value, we'll not say which position. We can do it that way also. But we'll say, I want to get rid of value 30, wherever it is. You with me? Somewhere in my list it is there. So I want to get rid of that value. How will I do? What will I do? Again, for delete, what you should do? You should position one step before. Correct? Okay, yes. See, if I say, okay, let's take this situation. My linked list consists of values, let's say, values. Now I'm not going by position, I'm going by value. say, so my HPDR is given. So this is my linked list. This is my linked list. Now, let's say I tell you, you have to get rid of 12. So delete 12. Delete the node whose value is 12, not by position, by value. So I have to get rid of this guy. So what should I do? I should position such a way that my next guy's value is 12 or whatever the value you have given me to delete. So I can check my next guy's value. No problem. We'll see how. So if that is the case, that I have positioned here, what should I do? I have to now, I have to take this guy out of the game. Correct? How will I do that? My next, I am here. Let's say this is T as an example. Just let's think it is T. So T is, sorry, I'll create a variable called temp, node pointer. Temp is equal to T next, next. This is a legitimate construct. T is next. T is next is this guy. His next is this guy. Correct? So in temp, I am positioning myself one step before, and then I am keeping a pointer to absorb the what T is next points. Why would I want to do that? Without that, I will not be able to take this guy out because I need this guy. What he is pointing to. Unless I get the pointer for this guy which I have to connect to this, I will not be able to take this guy out. So now what will I say? T is next. T is next is equal to temp. Correct? Am I right or wrong? So T is next is equal to temp. Now where is temp pointing by this? Temp is pointing over here. This is temp. T is here. Temp is here. Because temp is not T is next, but T is next. So temp is over here in this scenario. And I am saying T is next. This guy is next. Should be equal to temp. So is anybody pointing to this? No? No, nobody is pointing. So I can get rid of this. I will not show you how to get rid of it immediately. But now the link will be effectively this. So this guy is going out of the picture. Because in a linked list, I'll come from here to here and then I'll go here. So this guy, how to take him out? Go to his next guy and make this guy point to his next guy. I have to also free this, but don't worry about freeing right now. I'll add that color to this code in a little while when we are doing destructors a little bit and do that. Okay, we'll come there. But don't worry about freeing the memory. Just taking him out of the list is enough at the moment. So this is how I do it. Now here, what is the special case? Okay. The special case is again, if it's the first guy who is going out, where will T be? T cannot have a legitimate. Remember, what is T? The previous guy. If the first guy itself wants to get deleted, there is no previous guy, right? Huh? If the first guy is deleted, there is no previous guy. Does everybody agree? If somebody is at the top of the queue, previous guy doesn't exist. No? It's simple. You don't need computer science also. So, that case, I have to handle separately. Acha. If T is the last guy, how will I know he is the last guy? His next will be none. So, that again I have to handle separately. No, yes? Maybe not. It is the last guy and position one step before. So it may not be too difficult. Our standard loop may take care of that. But first guy, we have to be careful. Because first guy, Our HPDR is also going to change. Will change or not? Because the first guy itself is going to go off. So we have to handle that separately. Okay? So shall we try and write a delete? Okay, let's do that. Okay, so you have all the code we have in practice 4. Okay, if those of you who are not sure about your own code, please go on with practice 4. Those of you who are confident about your own code, continue with practice 3 or whatever you have. Okay. Yes? Okay. Those who are not confident, think you are at practice 4 and make changes with us and think with us. To go to the class and add a new method before display, we're going to add a method delete. Now, should delete return anything? Not necessary. No need. HPDR anyway will change. Okay. So we'll say delete. What should delete take as a parameter? The value. Value of the node that I want to get rid of. Okay. So int v. Int val. Okay. Now, as I said, we have to take care of the special cases first, and then we'll take care of the normal case. Special case is what? First node only has to go. How will you check that? HPDR's value, what is it called? HPDR's data. So HPDR's data, that means head pointer's data is equal to val. That means you want to knock off the first guy only. So we will start writing. If this is a special case, HPDR's data, that is head pointer's data, is equal val. Correct? If it is equal val, what does it mean? I am taking off the first node. Simple no. That means I am looking at the first node, that is I have to knock the first node out. So what should I do? I just have to modify my HPDR. Correct? What should I say? HPDR is equal to HPDR is next, whatever it may be. Done? Agreed or not? First guy is going out, so my new HPDR will be the second guy. So first guy will be forgotten. Actually, you have to free the first guy. We will not do the freeing now. I do a separate story and we'll decide how to free. Okay. Because I am waiting. For that we need to write a destructor in our node. Okay. And then I will show you how to write a destructor in a linked list. And we'll do that. Okay, that I have a separate session for that. So don't worry about freeing, giving up data. Just knock him out, take him out. That's it. Don't release that memory. Don't worry about the release of the memory. That's for a later day. Okay, so that's it. If HPDR's data equal val, HPDR is equal to HPDR next. Okay, I'll pause here and ask you this question. Let's see who, there will be some smart guy always is there, or smart person. Even in this code, there is a danger. Even if I am deleting the first node. What is the danger? Huh? If I delete it?
We are moving the pointer HPDR to the next one, but HPDR is still there in the memory.
No, don't worry about memory. Huh? Length is? Length has to be decreased. Yes, I agree. We have to do that. No, that is a care you have to take. Agreed, we'll do that. Good point. But there is something danger in that line. 83. I have written it casually. Something is dangerous about that line. Can you tell me what? It's important to know. That differentiates a...
What is HPDR next in math?
What? Can you improve that?
HPDR, it is the only element in that.
Okay, can you further improve it? Or if it is a zero node linked list. Suppose my think like this. Suppose my linked list is completely empty. And I say, delete some value. Can you visualize it? I have not done any append, I have not done any insert, nothing. Are you with me? So my HPDR is what? Null. I have not done append, I have not done insert, but I have said delete some value. Then the line that you see on line 83 is a very dangerous line. Why? Because on a null pointer, if you try to do a access, it will give you a segmentation fault. That means HPDR itself is null. And what are you trying to do? On that HPDR null, you are trying to access its value. You can never do that. C++, we can try that if you want. Okay? We'll try it. We'll leave it like this. But to make it safe, what should I do? I should first say, I should do this code only if HPDR is not equal to null. So I should say, if, no, I will not make the change now, HPDR not equal to null, and then you can say that. And means, once this statement is true, then only it will go to the next line. Remember the beauty of and. And what happens? The second statement will not be executed unless the first is true. If the first itself is false, it doesn't have to execute the second. No? The truth value is established there only, that one false is enough to make an and false. Okay? So we can cleverly write, or you can write an if loop. Okay? But a more subtle and a nice way of writing is, check whether HPDR is not equal to null, then only write this line. So you can put it in an and. Okay. No. I mean, right? So here I am pretending that HPDR has a legitimate value. At least there is one node in the list before you try to delete. We will take care of that situation later. So HPDR is a HPDR length, and as some person pointed out there, we have to also reduce the length of the list, which we have forgotten to do. Okay, so we will have to say inside 85 length minus. Then this is if you are taking care of the head. The guy who is inserted is at the head. Okay. Else is not at the head. So I have to position myself starting with temp. I have to keep moving forward. So let me write that code. Let me have a temp equal to HPDR. Remember, I should not disturb HPDR. So else while temp not equal to null. Correct. First we should check temp is not equal to null, and understand this condition. I will elaborate it now. While temp not equal to null and temp's next is the next pointer. Remember? Now, are you understanding what is temp's next? It's a pointer to the next guy after temp. His data. So I should say temp's next data not equal to val. Okay. What should I do? Did you get this code? Did you understand what I have written? While temp is not equal to null. Temp should not be equal to null. Temp is equal to null means I have gone beyond the list. While temp not equal to null and temp's next means this guy is next. We are starting from the head. Next, that guy is data. My next data is not equal to val. Remember, my objective is to stop one step before. So that's why I am saying, is my next data equal to value or not? That is what I am saying. Because I can't stop at that node and delete it. No. You can't stand on that and say go. No, you can't. Stand one step earlier. Mandatory. Yes.
Yes.
Everybody agrees? Okay. So, I will say while temp not equal to null and temp's next data not equal to val, I continue to move forward. That is, I have not reached where I want to reach. Temp is equal to temp's next. Correct. Now, when I come out of this loop, one of two things may have happened. What is this one of two things? Either temp may be null, that means what I am looking for is not there. There is a danger there also. We will not watch. I should actually say that if temp's next is not equal to null, I should say there while temp not equal to null is not correct. That is, I should say temp's next. You know why? Think about it. Remember, I have to stop one step before. Do you agree with my correction? I have to stop one step before. So my temp's next should not be equal to null. And temp's next val, temp's next data, that is the data sitting in my next node, should not be equal to val. Till then I am going forward. Now, when I come to line 92 after the while loop, what is the reason I have come here? Two reasons. Two reasons. Either temp's next has become null, that means I don't have a value in the list, correct? It's not there. So there is a question of deleting, correct? Or I have positioned myself correctly. Agreed? My next, if it is equal to null, means I have already reached the end and there is nowhere to go. I can't go forward now. Forward is null. So, I will say if temp's next equal null, I have to say C out element not found, data not found. We are in that else only, we are in that else loop. You can have any level of nesting, no problem. Okay? Achha. This has not happened. Else means what? I have come out of the loop, but I have not reached null. That means I am correctly positioned. What should I do now? That means I am before the guy. My next data is equal to val. So I am before that guy. And who is pointing to that? Temp. Temp is pointing. So now what will I say? Now temp is positioned before. Now what do I need? I need my next. Yes, no. That should become my next. My next node's next should become my next. That is how I will kill the next guy. Correct? So my next. So else. Now I might have to no, I think this can be done in one line. No? Temp's next is equal to temp's next. This is a slightly dangerous line. We leave it here. Then I'll ask you at a later point why I should not do this. Right now it is okay. I have lost that in between guy. We have tons of memory. Okay? Let's pretend that we have infinite memory. Okay? So, temps next is equal to temps next next. That is, we are jumping, that our next guy is going away. I am now pointing to his next guy. Okay. And we are now, the list is complete because now the pointers are adjusted accordingly. Because my next has become my next next. Okay. Are we done? Yes? It's not very tricky. What I am doing is, I am handling only two conditions. If it is the first guy who has to get deleted, I have to do it separately. If the in-between guy who is getting deleted, I have to do it differently. While doing that, I have to check, I have also a situation where the element that I want to delete is not on the list. So what do I do for it? And how do I detect that condition? Okay. So we will try our luck. Length has to decrease in every case. So here you have to decrease in every case. Yeah. So length you have to decrease in every case. You have to be careful with the length. In every case means both the cases. When head is going away or some in between guy is going. When a legitimate L dot delete 15. 15. Why is delete coming in different color? Then don't say delete. We are in C++. We can't use delete. Delete. We'll say remove. Delete. I just skipped my mind. In C++, delete is a reserved word of the language, so you can't use delete. Don't use it. Just change delete to remove. Not delete. Okay, fine. We are writing it as not delete, whatever name. Remove is also fine. Okay, yeah, seems to be fine. So, can you make it bigger? Okay, so see this. After insertion, it was 5, 10, 15, 30 and 20. Then after deletion of the node 15, we have 5, 10, 30, 20 as expected. Clear? Now I have taken only one situation where we are deleting in the middle. You can try deleting in the beginning also. I leave it to you. Okay. Please try that. If you delete in the beginning, what happens? Is our code working fine? So now what I will do is, I will give you this code. So those of you who are not able to follow in the break, please look at it and then we will continue. Okay. So we will give you this code as 5. Those of you not still struggling with code, in the fond hope that you will catch up soon, please take practice 5 where we have incorporated this code. Go back, refresh, you will see practice lab 5, open practice lab 5, whatever code we have just written in front of you is there, please go through that code. That is also available to you at home.